Okay, looks like we're live here. And just make sure I don't have the same audio issue from last week. Sounds like I don't, so that's good. All right, so a couple of people had left some questions last week. The main question, of course, was just, how do I get a 36? And the biggest concern actually was, hey, I do really well in my classes at school. Why am I not doing a heck of a lot better on the ACT? And so I'll try to address some of those things today. Jack is back. That's a good sign. And of course, yeah, if you have specific questions from certain form codes, that's a little bit more helpful. Somebody on Reddit asked me, can you go over functions? Which is basically all of math. So I can, but it helps if we narrow the focus just a little bit. Let me bring the chat in there. It says, took my ACT, felt a lot better this time around. That's good. I think you had said you were taking it on Wednesday, and I heard mixed reviews from that exam. That some people said it was really good, some people said it was really rough. So I know it'll be a few weeks before you get your score, so hopefully that went well. Of course, everybody struggles with the reading and the science portion, so if we don't have any specific questions, I'll just get into dealing with some of those passages. In particular, the science portion. I've got ACT A11, and there's some science questions that we might wish to go over from that exam. Actually, better yet, ACT B5. That's a little more recent, from December of last year. Soon the February test release will come out, so that'll be nice. I can see exactly what everybody was complaining about on Reddit. Said there was a matrix problem, just like we went over. That was good. And like I said, everything is really predictable on the ACT, especially the math portion. People are like, what do I do for the math section? I don't know what to study. You go back and you open up your textbooks from previous classes, because if you covered matrices in Algebra 2, or some classes cover them in pre-calculus, some people don't cover them at all. If you covered those in Algebra 2 and you got a C on the matrices exam, and then your teacher kept moving with the next unit, you never got an opportunity to improve your understanding of matrices. So go back and review, right? That stuff that you didn't do so hot on in the past isn't just going to go away because it's out of the way in your class at school. Okay, so I'm looking at the December 2018 exam, and I'm just going to bring in a couple of questions from the science portion there, and we'll just go straight into passage 1 and play around with the first couple questions. Again, nothing on the ACT is tough, and that's really the most important thing to realize, is that when you see these questions and you see these passages, it's really easy to get quickly daunted, especially, for example, let's say you have never covered equilibrium in chemistry. Then if you see this passage and they're giving you stuff about the equilibrium constant that you've never encountered before, that might be a bit of a struggle, just again based on what you see visually. It's unfamiliar to you, and that's okay. The thing that you have to realize, again, going in, is these are not difficult questions, right? They may give you something that's totally new. You may feel blindsided by it, but they're not going to ask you anything that requires you to actually understand chemistry or bring in a big physics background or something like that. So if you see this passage, your first instinct should either be, if you've taken AP Chem, your first instinct should be, great, I'm excited to do an equilibrium passage. But if you haven't, if it's unfamiliar, your first reaction should be, oh goodness, I'm scared. And then about half a second later, you should say, okay, it's the ACT. I know it's going to be easy, so let me kick this out of the park. The first thing to do whenever reading any of these passages is to remind yourself that most of the information there is totally unnecessary, right? You've got these charts, you've got these figures, you've got this background information. a lot of it is not going to help you to answer the questions. So for the reading, I generally like to read the whole passage, but when it comes to the science portion, if you read the whole passage, you're usually putting yourself at a disadvantage for time. So because the questions are so specific, just go straight to the questions and then piece together information that's new to you as needed, right? As you need it. So for example here, I would just go straight to question 1. It says, according to table 1, if you see table 1, go to table 1. And importantly, sometimes those science passages have multiple different passages. Don't necessarily assume that table 1 is the table that goes with passage 1, right? Or scientist 1, what have you. Make sure, obviously, it says table 1. Okay, so it says in trial 5, what was the equilibrium concentration of Z? Okay, so it tells you here, table 1. Okay, so I'm going to go to trial 5. This is a really easy question. What's the equilibrium concentration of Z? So I noticed that along the axis here for the table, they give me something to do with Z. It's in moles per liter. That may be unfamiliar to you, right? You may not know what that means, that bracket. No problem. It tells you here that brackets indicate the equilibrium concentration of the substance. Okay, so again, foreign information, but presented to you in a really intelligible and easy to understand way. Z, trial 5, table 1, it's 0.5, right? We know that those units are moles per liter, so we're good. And we move on, right? Nothing involving the passage there except for, oh, I ran into a small problem. I don't know what these brackets mean. I know the passage is going to tell me because the ACT is easy. And I'll just look at question 2 as well. It says, suppose we had done trial 7, but we had conducted it instead at -5 degrees Celsius. Based on table 2, what would K have been? This is a very common type of ACT question that deals with interpolation or extrapolation, right? If we did one more experiment, we kind of extend out the trend, what would we have seen? So it says trial 7 based on table 2. So I'm looking at trial 7 based on table 2. And I want to know, what if it had been done at -5 degrees Celsius? So we see a bit of a trend here. The equilibrium concentrations of X, Y, and Z definitely differ with temperature. And it looks like the only independent variable, which is usually, by the way, on the very left-hand side of a table, looks like the only independent variable there is temperature. And so we want to know, what if the temperature had been -5? Well, okay, in between -15 and 0 would fall -5. So I would expect that K for those would fall somewhere in between 0.59 and 10.5. And unsurprisingly, only one of the answer choices here, namely choice H, actually falls within that range. Okay, make sure that the only independent variable in that experiment is temperature. And if I go back into the passage, it tells me, hey, there were 10 trials, 1 through 5 were the same temp, 6 through 10 were at different temperatures. So that's really the only difference, right? They don't give us any indication elsewhere in the passage that anything would differ from trial to trial. Okay, so an easy way to reach choice H there. Okay. A lot of people struggled because it asked a specific question or two that we needed background knowledge. It's asked what a protein is made out of, and there was nothing in the text that said there was amino acid. So what I would say for that, and some students with the newer science passages do struggle with kind of outside knowledge questions. The outside knowledge questions are pretty predictable insofar as what they expect you to bring to the ACT from your science classes or just general science knowledge. And they've actually asked in the past, they've had the science passage was competing scientific hypotheses on the nucleic acid hypothesis versus the protein hypothesis, and they actually asked you, which of the following diagrams would represent a protein, right? And it was a chain of AAs or amino acids. So oddly enough, that's actually something that they've asked about before. That's also, you would probably think, okay, that's a really kind of minute detail back from when I took biology, whenever you did. I majored in biochemistry, so to me, that's a really big deal, right? I would want everybody to know that proteins are made of amino acids. But that said, to extrapolate your statement into more of a question, a big concern that students have is, okay, what do I have to know from the outside? So let me just write a few of these down so far as outside knowledge is concerned, and then we'll come back to this passage because I think it's a good one. It's very indicative of of the types of data analysis questions that the ACT will give you. Okay, so just a couple of background information or kind of outside knowledge, right? Okay, so stuff you need to know from the outside for the science portion. Really, we can break things down into biology, chemistry, and physics. Okay, everything else is going to be within the confines of maybe earth science, where you need to know the layers of the earth, right? Crust, mantle, core. Hopefully you know those back from 5th grade. If you don't, go know them. But for the most part, the outside knowledge stuff that they'll ask you is kind of related to biochem and physics. So just a couple of things. Let me start with biology, just since that's what came up. Let me get inside the frame here. So for bio, the biggest thing that comes up for outside knowledge is Mendelian genetics, right? You have to understand genotype and phenotype. You have to understand how to do Punnett squares and maybe mono or dihybrid crosses, and to interpret the products of a cross in terms of the phenotype, right? So you need to know how to do, like I said, Punnett squares. Okay, if that's unfamiliar to you, then that's not a good thing. You need to know how to do, like I said, you really should have an understanding of kind of basic Mendelian inheritance. Mendelian inheritance basically just means you either have simple dominant or simple recessive traits, right? So in other words, big A equals, big A, little a, the homozygous dominant equals the heterozygous, which does not equal the homozygous recessive. So really basic stuff so far as patterns of inheritance are concerned. You also need to know cell parts. Okay, and that's not just limited to, oh, the mitochondrion is the powerhouse of the cell. You need to specifically know that the mitochondrion does cellular respiration, right? It produces ATP from glucose. If that's totally unfamiliar to you, go back and look that up. There's been an outside knowledge question that required you to know the formula for cellular respiration, right? There's been another one that required you to know the formula for photosynthesis. So don't just know that the chloroplast does photosynthesis. Go a little bit step further. Make sure you know what photosynthesis is actually accomplishing, right? You're turning carbon dioxide and water into sugar, okay? So cell parts you definitely need to know. You should know the lysosome. You should know ribosomes. You should obviously know the nucleus. And then you should know, again, the mitochondrion and the chloroplast. You also need to know your macromolecules. Okay, some of you, if you're weightlifters or bodybuilders, you talk about your macros, right? Your lipids, your fats, oils, steroids, and waxes. Your carbohydrates, your starch and your sugar. You talk about your proteins, and you talk about your nucleic acids. And for each of those macromolecules, you need to know a couple of things. You need to know their function, right? What do they do in the cell? What are they used for? You need to know their monomers. So for example, you should know that proteins are made up of amino acids, nucleic acids are made up of nucleotides, and you want to know a couple of examples, right? So if I give you, for example, I tell you I'm dealing with olive oil, and I ask you what type of macromolecule that is, you should be able to identify that as a lipid, okay? So those are a few things from biology that seem to come up pretty frequently. The Mendelian stuff and the Punnett squares more than anything else I've seen come up. But now this is probably the second or the third time that macros have come up as well. So just be aware of that. It says the last section of science was so tough. I guessed on every single question. Okay, that's not good. Specific things about electrons and neutrons and some chemicals. How many electrons? Okay. Well, that naturally takes us to what you should know in terms of outside knowledge for chemistry. Okay, so let's think about that. For chem, it's really important, first off, that you understand atomic structure. Okay, you need to understand how the atom is structured. You need to know that the atom has a very dense, positively charged nucleus, right, and that nucleus consists of protons and neutrons, and that it's surrounded by, and this is a really bad model, right? The Rutherford model has, since been debunked by the quantum mechanics, but you need to know that it's surrounded by negatively charged electrons, right? Of course, if we're neutral, right, if something is neutral, that means the number of electrons equals the number of protons. If we change the number of protons, right, so we change the number of protons, that's the atomic number, that defines what element we're talking about. So for example, if there's 1 proton in the nucleus of an atom, it's hydrogen. If there's 4, then I think that's beryllium, right? If I change the number of neutrons, okay, that defines the isotope of a particular element, right? So you've encountered isotopes before. Very basic. Now, if I take away electrons, then I have less negative charge. So if I take away electrons, right, I remove electrons, or some of you remember that as oxidation. If I remove electrons, then I generate a positively charged ion. We call that a cation. Okay? And of course, the number of electrons that I remove gives me the amount of positive charge left over. If I were to add electrons, right, or again, you remember that's reduction. If I add electrons, that generates a negative ion, and we call that an anion. Let me move that over for you. Okay, again, the number of electrons that you add, right, the extent of the reduction that you do, gives you the total charge, right, gives you the valence difference, right? So for example, if I tell you I have carbon, and I tell you that carbon characteristically has 6 protons, and I want to know what like C2 minus looks like, and I ask you, okay, well, how many electrons does that have? Well, I'd start out by saying, okay, well, carbon, for example, neutral carbon has 6 electrons, right? Because the number of electrons must match the number of protons. And so C2 minus has got to have 2 more electrons than carbon, so I've got 8 electrons. Okay, I know this is not super complicated for you to understand, right? This is probably not news to most students, but the issue is that when you're thinking about preparing for the ACT, it can't escape your mind, or it can't escape your notice that you need to know your fundamentals from chemistry. You need to know your fundamentals from biology. They will be on the exam. Okay, let me just say a couple more things about background that you need for chemistry. One really important thing is that if they give you a formula, okay, it's very likely that you're going to use it. Okay, so just because I mentioned it earlier, let me give you the formula for cellular respiration, for example, right? It's basically just the combustion of glucose. And if I were to see this formula, I would expect some sort of question about it, okay? And the question that they'll usually ask is, over the course of the experiment, what happens to the concentration of a particular substance? Okay, so all that really matters is that you know that if I've got these boys over here, these are reactants, over the course of the experiment, their concentration is going to go down. Right? That's what it means to be a reactant. It means to disappear and turn into product over time. And if I look at the product side, the concentration of these is going to go up over time. I've seen these questions asked quite a few ways on quite a few different exams. People tend to struggle on them. So again, go back and make sure you know your fundamentals. Okay, I'll divert and answer your polynomials question here. But another thing before I do, on chemistry, and I won't go into it so much here, but I want you to be aware of the fact that you need to know it. Another thing that you need to know is colorimetry, okay? Colorimetry is huge, and I've seen probably 10 to 15 questions, or passages rather, relating to colorimetry in some regard on the ACT. Colorimetry, maybe if you've done this in class, you may have also called it spectrophotometry, right? Spectrophotometry. And basically, these are those passages where I've got a solution. Let's say I have a solution of cobalt. Okay, let's say it's cobalt ion, and I shine light onto it, and only some of the light makes it through, and this allows me to, for example, determine the concentration of cobalt ion in solution. For those of you who took, I believe it was the April 2017 exam, there was a passage where you were looking at iron 2+ ion, and this is the one where they added O-phenanthroline, right? So there was just this random other chemical that was added to it, and and they combined to make some orange substance that absorbed light depending on the concentration of the iron. Again, I won't go too much into it right now, but I would highly recommend that you either find a spectrophotometry section in a chemistry textbook, or that you go onto something like Khan Academy. Maybe I'll post a video about colorimetry specifically later, but I'll just put a big star next to that. That's something that comes up really, really often, so make sure you know it well. Okay, you said there was a question on the ACT. Divide a 5th degree polynomial by x minus 2 or x plus 2, something like that. Yeah, so let's divert from the stuff on background knowledge really quickly and look at basically what you're talking about in general are called rational functions. Okay, and rational functions are basically, you know, functions that contain a ratio of other functions, okay? So you can just generalize that a rational function, let's call it r of x, is equal to some polynomial p of x divided by some other polynomial q of x. So I'm just going to kind of go down the line and cover all of the types of different questions and topics that you need to know relating to rational functions. Oftentimes what they'll ask you is to determine the asymptotes of a rational function. Okay. Obviously, if you've got your calculator, that's a pretty easy thing to do. If you don't have your calculator, you still should understand the ideas behind determining asymptotes. Okay. So again, I want to figure out the asymptotes of a rational function. If I'm looking for the horizontal asymptotes of a rational function or the vertical asymptotes, let me start with vertical because that's a little bit easier. The vertical asymptotes are when a function approaches positive or negative infinity, okay? And the only way that this right here, this quotient would approach infinity is if the denominator approached 0, okay? Now, of course, the numerator could approach infinity at some point, but not asymptotically. Okay, asymptotic behavior toward infinity is going to occur when the denominator gets really, really, really small, right? If the denominator is 0.000001, as they get even closer to a small value, the total quotient is going to shoot up exponentially. So this is when q of x is equal to 0. Okay, for the horizontal asymptote, that's a question of what happens at infinite behaviors for x. So if you've taken calc or finished pre-calc, this is basically the limit as x approaches plus or minus infinity. Okay, so I'll assess that in a non-calculus way here. So let's say, for example, I give you some function fx is equal to x squared minus 7 over x plus 4. All right, so just kind of a dummy function there. The first thing that you do not want to do here is just think about graphing it in your head. Okay, that's not a good idea. If you have your calculator, then go ahead and graph that. It'll do all of the dirty work for you. But if you have to figure out asymptotes, you should be able to do this by hand. So for a horizontal asymptote, right? If I have a horizontal asymptote, again, that's what happens when x gets really, really big or really, really big but negative, okay, as it approaches plus or minus infinity. So importantly, there's 3 cases here. There's the case when the degree of the numerator is greater than that of the denominator. There's the case when the degree of the numerator equals the degree of the denominator, or when it's less than that of the denominator. And degree simply means the highest power, right? So for example, the degree of this polynomial is 2. The degree of this polynomial, if we write it in, is 1. Okay, so for this particular example, I've got a situation in which the degree of the numerator is greater than that of the denominator. Okay, in this situation, there's no horizontal asymptote. Okay, you'll have what's called a slant asymptote, and ACT will not test you on slant asymptotes. All right, they'll ask you that in a different way. They'll never ask you for slant asymptotes. So if you've got the degree of the numerator greater than that of the denominator, no horizontal asymptotes. Okay, so again, just to be very explicit here, no HA. Now, if the degree of the numerator equals that of the denominator, then as x gets really, really big or really, really negative, okay, let's say, for example, I have x squared plus 4 over x squared minus 7, okay? And there could be an x term as well here. In fact, I could just do plus 3x, okay? It won't make much of a difference. So, looking at the numerator and the denominator here, because they're both of degree 2, as x gets really, really big, the top and the bottom are pretty much the same. right? And the reason for that is that as x gets really, really, really big, and indeed as it approaches infinity, x squared is infinitely bigger than 3x or 7, right? So those terms effectively just don't matter, right? And so when I have the degrees equal, I can just compare the coefficients on those leading terms. The leading term is the term that has the highest power. So if this, for example, is A and this is B, then the horizontal asymptote is going to be y is equal to a over b. They effectively just cancel out. Okay, that's going to be a horizontal line, and it's just the quotient between those two leading terms, the coefficients. Okay, and if the numerator's degree is less than that of the denominator, I'll just be very straightforward and quick here. You have a horizontal asymptote at y equals 0, right? If the degree of the denominator is bigger than the numerator's degree, let's say I have, for example, x over x squared plus 4, right? Then as x gets to infinity, the numerator is infinitely smaller than the denominator. So really big denominator compared to an infinitely smaller numerator, that's just basically 0, okay? So that's pretty straightforward. Vertical asymptotes are even easier to figure out. A vertical asymptote is just when is the denominator equal to 0, right? When's the denominator equal to 0? After you factor and simplify. So first, factor, second, simplify, and then, right, then figure out when the denominator equals 0. Okay, so again, back up here, I had q of x. So whenever q of x is equal to 0. In that situation, you've got a vertical asymptote. Okay, so let's actually take a better example than the one I gave. Let me give you something like fx is equal to x squared minus 4 over x plus 2 times x minus 7. Okay, and actually make that x plus 7 on top, okay? So the first thing that you want to do is factor, and this is a really straightforward one, right? I've got a difference of 2 squares in that numerator, so that factors to x plus 2, x minus 2, and then I've got that x plus 7. And then on the bottom, I've got x plus 2 and x minus 7. Okay, so really importantly here, my x plus 2's cancel. So x equals minus 2, that would make this 0. That is not a vertical asymptote, okay, because it cancels out after I factor and simplify. What we actually have there is what's called a hole when x equals minus 2. Okay, now the actual point at which there's a hole, I'd have to plug in minus 2 to the function and see what it would be, but that is not an asymptote. My vertical asymptote would actually be x is equal to 7, because that would make this factor on the bottom equal to 0. Okay, so asymptotes come up really frequently. Make sure you know how to do that. Another thing that comes up with these is how do I divide them? Right? How do I divide rational functions? So if I have, for example, x squared plus 7x minus 3, let's divide that by x minus 2. There's a couple of ways to do this. One way that you can do it is just by long division. Okay, so if I were to go just like I would divide any actual numbers, because, hey, a polynomial is a number for a given x value, I could set this up just like long division. Okay, and so I'm going to take this x squared, right, the big term inside, and divide by what's outside, right? X squared divided by x is x, and then just like I do with normal long division, I'm going to take that value on top, multiply it through here, and subtract it from the original value under the bar, if you will. So if I multiply x by x minus 2, I get x squared minus 2x. Again, just like normal long division, I subtract, so my x squared goes away. Minus 2x would be 9x. Minus 3, you bring that down, just like normal long division. And then you repeat the process, right? So 9x divided by x, that's positive 9. 9 times this here is 9x minus 18. Go ahead and subtract that again. And the 9x cancels, and I get here plus 15. That's my remainder. And so that's going to be plus 15 divided by x minus 2. So that is the quotient of those two rational functions. And importantly, these are equal, right? These are equal to each other. So if I want to graph this or graph this, it's the same value, right? It's the same exact function. So any assessment I can do on one, I can do on the other. And sometimes one is easier to understand in one form than the other is. Now we can simplify or streamline this process by using what's called synthetic division. And in that case, you just write out the coefficients, right? So this is 1x squared, 7x minus 3. So 1, 7, minus 3. And for whatever reason, we drop the bar here. And we're dividing by x minus 2. So the root that we're pulling out is 2. Right? The root that we're pulling out is 2 because it's x minus 2. If that were x plus 2, this would be negative 2 here. We drop down that 1. And we multiply this 2 times this 1, 2. And then we add, not subtract. So it's 9, that's 18, and this gives me my 15. And what this 1 means is, okay, well, that's 1x plus 9, right? We're decreasing power from the original, plus 15 over what it is we're dividing by, and that's x minus 2. Okay, so again, synthetic division, it's the same process, right? Synthetic or long division. Synthetic division, you don't have to worry about throwing the variable names in there. It's kind of like matrices, how they take the variable name out and just leave behind the coefficients. You said you want to divide 7x to the 5th minus 8x cubed plus 3x squared minus 14 by x plus 2. Okay, so let me do that problem. You say 7x to the 5th minus 8x cubed plus 3x squared minus 14, and we want to divide this by x plus 2. By the way, if this factors out evenly, right, and I find that the remainder when I divide is 0, that means that that's a factor of the original polynomial, right? So the value that I took out here, 2, if the remainder here were 0, then that would be a 0 of the function, right? I know that I plug that in and the value is 0. Okay, and here again, if I had divided out x minus 2 and the remainder had been 0, then that means x minus 2 is a factor of that polynomial. All right, a kind of converse to that, or an extension of that, is that we have what's called the remainder theorem, and that states basically that if I divide any polynomial by a linear monomial, the remainder is the value of that function evaluated for that particular root. Okay, so let me just say that really quickly. If I have p of x divided by x minus r, and this gives me some product, right, some quotient q of x plus a remainder over x minus r, right, that's kind of the form that you get when you do long division, then this remainder r is p of little r. Okay, so the function's value for any given input is the same as the remainder if you divide it by x minus that input. Again, that's called the remainder theorem, and that's really helpful for solving some problems, at least on occasion. Again, the remainder theorem. Okay. They'll also ask, for example, if I have a polynomial and I tell you, okay, minus, this is the original, right? It's minus 14k. Well, what does k have to be so that this is a root? Well, I can do synthetic division on this, and then when I get my remainder term, set that equal to 0, because I know from the remainder theorem that that means that that particular monomial, right, x plus 2, is a root, right, because the remainder is 0. In other words, f of that root is a 0. Okay, anyways, let me just do this really quickly. The k was not there. So how would we do this? The biggest mistake that people make is they forget that here is a 0x to the 4th term, and here is a 0x term, right? They'll forget that those terms are buried in there, and they'll forget to write them out when doing the long division. They won't hold a space for them. Okay, so I'm just going to do the synthetic division because it's the same thing and it's a little bit quicker and the process is the same. So I'd have 7. Importantly, 0 is my coefficient for the x to the 4th term. And then I would have minus 8 for the x cubed term, 3 for the x squared term, 0 for the x term, and then minus 14 for the constant term. And if I did synthetic division, I would divide out minus 2 because it's x minus the root. So I drop down my 7. That product is minus 14. I add minus 14. This is 28. I get 20 here, minus 40, minus, these are odd numbers here, not helpful, 74, and minus, that would be 148, and I add those, minus 162. Okay, this is not a nice one. Let me just make sure I did that correctly, right? If you get weird ones like this, you might go, wait, maybe I did the arithmetic wrong. That there is positive 28, that makes 20. Yeah, it looks like this is correct. So what this would mean then is that the quotient, right, I dropped the power 1. If I'm dividing x to the 5th by x to the 1, the product is going to be of degree 4, right? Something x to the 4th. I'm lowering the power by 1. So this would be equal to then 7x to the 4th minus 14x cubed plus 20x squared, right, minus 37x plus 74, and then that remainder of 162 would be minus 162 over what we divided by, which was x minus this value, so that would be over x plus 2, okay, which is sensible because we're dividing by x plus 2 here. Okay, so you probably wouldn't get as complicated a long division or synthetic division problem on the ACT. Again, the big mistake that you want to watch out for is not remembering that these coefficients, right, on your x to the 4th and x terms there are both 0. Okay, so if you do the synthetic division and leave off this column, you're going to get a totally different and importantly wrong answer. Okay, so that's the big mistake that people make with those. If you want to do more practice for these, again, what you should search for would be rational functions. Right, and that's going to be a big section in any Algebra 2 or pre-calculus textbook. You need to understand how to do asymptotes. You need to understand the remainder theorem. That's something that you would find definitely in an Algebra 2 textbook, along with, like, you know, end behavior for polynomials and Descartes' rule of signs, the rational roots theorem, all that good stuff. And again, you need to know how to do division. Okay, I'm assuming you know how to do multiplication, and that's because that's something that you do in pre-algebra in like 5th or 6th grade. So know how to do both of those forms of division and use them in conjunction with the remainder theorem, right? If you get a remainder that's 0, what does that mean? It means that the thing you divided by is a factor of your function. So you can use that to your advantage pretty often. Okay. Let me go back to what I was saying earlier about the background information that you need to have for some of the different sections. Namely, we were talking about some background that you need to have for chem. Again, on your own time, go and look into colorimetry. That's something that comes up on the ACT very often. Just a few more things. If you encounter a quantum mechanics passage or something about muons and gluons and fermions, right? That is not something that you cover in a traditional chemistry class, certainly not in a high school general chemistry class. So that should clue you into, hey, I probably don't need to actually understand what these things mean. I just need to see what's going on in the passage, right? The passage will tell me everything I need to know. So don't be daunted. All right. A couple of other things with chemistry. You should probably know what some of your chemical symbols mean, right? So there's absolutely no reason to have memorized your periodic table. But if you see Na and don't know that that's sodium, that's a bit of a problem, especially because I could see the ACT asking you a question where they give you Na and then they'll ask you about sodium. So just, you know the symbols probably of the first 2 or 3 rows of the periodic table. Just recognize what those names are. Know obviously what the difference between a metal and a non-metal is, right? If you see a periodic table, you should have some understanding of what that means. And then finally, a topic that comes up really frequently that I wish more students would know both for the AP exam and just in general is the idea of electronegativity. Electronegativity, by definition, is an element's attraction for an electron within a covalent bond. And basically, if you've got a high electronegativity, it's really tough to take away an electron from an atom. If you've got a really low electronegativity, it's very easy to take away an electron from an atom. So for example, metals have a very low electronegativity, whereas nonmetals like fluorine, chlorine, oxygen, nitrogen, etc. Have very high electronegativity values. That's a value that you don't need to memorize, but is at least an idea that you need to be familiar with, okay? Comes up in lots of different ways, so just understand that if something is really willing to gain or lose an electron, it's really reactive, because that's really all a chemical reaction is, right? Gaining or losing electrons. Okay, a couple of other things. You need to know some outside knowledge for physics, and the problem with physics is most high schoolers avoid physics. And probably for good reason. There's not a lot of good high school physics teachers. There are a couple of kind of formulas and values and definitions that you need to know from physics, so I'm gonna detail those for you here. You want to understand the idea of energy. That comes up very frequently, and energy comes up in a couple of different forms. So there's kinetic energy, which is the energy of motion, right? And to calculate that, right, we say Ke is 1/2 mv squared, where m is an object's mass and v is an object's velocity. Okay, not volume. For whatever reason, I've had somebody try to calculate that with volume before, and that does not work. Importantly, the units for energy, at least in the SI system, are joules, right? That's the standard unit of energy in the SI system. Mass is given, for example, in kilograms. Velocity would be given in meters per second, so you can get a feel for the fact, if you plug those values in, that a joule is a kilogram meter squared per second squared. Okay? Anyway, so kinetic energy, you need to know that formula, right? Just know it. They ask questions about kinetic energy all the time. If an object is moving faster, it has higher kinetic energy. If two objects are moving at the same speed, the one with the greater mass has the greater kinetic energy. Okay, for example, consider a baseball going 5 miles an hour and a train going 5 miles an hour. There's a lot more energy in the train going 5 miles an hour, specifically because its mass is a heck of a lot higher. There's also potential energy. Potential energy is stored energy, and it comes in a number of different forms. There's chemical potential energy, and that's just the energy that's stored in a bond, and I don't think you would ever need to calculate that value. There's also spring potential energy, where I have the spring potential energy, PES, is equal to 1/2 kx squared. That's really easy to remember because it's just like the formula for kinetic energy, except two different values. For 1/2 kx squared, k there is just a constant, right? It's a spring constant or the stiffness constant, and x is how far you stretch or compress a spring. Okay. And then lastly, the one that they'll ask you about is gravitational potential energy. This is the one that comes up most frequently, and that just relates to an object's position, right? Positional potential energy, how far an object is off the ground. So there, the potential energy due to gravity is equal to mgh. And m there, again, is mass. Move that up. M there is mass. G is just a constant. It's the acceleration due to gravity. That's 9.8. Units are meter per second squared, and then h is height off the ground, right? How far above the ground are you? Okay, so in thinking about conservation of energy questions, conservation of energy, let's say I take, for example, a block that weighs 1 kilogram here, and it's 1 meter off the ground, and I drop it, and I want to know, okay, when it hits the ground, how fast is it moving, right? How fast is it moving when it hits the ground 1 meter below? Well, what I can do is appreciate this in the context of energy. Because at this position, it has some amount of energy. We say a certain amount of mechanical energy. And that mechanical energy is just its potential plus its kinetic energy. And so its mechanical energy here is going to be its kinetic energy. If it starts from rest, the kinetic energy is 0. And it's got some potential energy due to gravity there. And its potential energy due to gravity is mgh, right? So m there is 1, and g there is 9.8. That's a constant, more or less. And h, the height above the ground, is 1, right? 1 meter. Then, when it gets to the bottom of its fall, its kinetic energy, well, I don't know what that is, but I do know it's 1/2 mv squared, okay, whatever that happens to be at that point. And I know that its potential energy is 0, right? If you're 0 height above the ground, your potential energy due to gravity, of course, is 0. And importantly, conservation of energy says, hey, these two values are the same, right? That energy is conserved. The amount of energy we started with is equal to the amount of energy that we end up with. That's more or less true, right? Friction, air resistance, that'll take energy out of a system, but more or less as an approximation, those are equivalent. So if I want to know the value of the velocity at the bottom, I say, okay, well, the potential energy at the top, that was 9.8. That's got to be equal to 1/2 mv squared at the bottom because the energy is conserved, which means, of course, here, and m there is still 1, right? The mass is 1. Which means that v, just simple algebra, would be the square root of 2 times 9.8. Okay, whatever that is. So plug that into a calculator, you get your v. The important thing again there is that we say energy is conserved. Now, notice that about halfway through here, right, if we're halfway through its fall, some of that potential energy from the beginning has been converted to kinetic energy, right? So here, right, let's say we're at 0.5 meters above the ground, then the potential energy here is half of what it started, and that difference is now the kinetic energy, okay? So again, as we're falling, if we get to 0.5 meters, the kinetic energy plus the potential energy at this point, right, is going to be equal to the potential energy at the top, right? Because the energy, if we're assuming it's conserved, has to be equal at all points. Okay, so that comes up pretty frequently. Another thing that you need to be aware of is the idea of momentum, right? Momentum. And momentum is just another quantity, right? Momentum, for whatever reason, gets the formula P, or the symbol P, I don't know why, and it's equal to just m times v, right? So here, momentum is equal to simply mass times velocity. And the units there are just kilogram meter per second, right? Because mass here is in kilograms, velocity is in meter per second, so momentum is in kilogram meter per second. Momentum has come up in a few places. Know that formula, right? Don't miss a question about momentum just because you don't have the formula remembered. Notice again that if an object has a higher mass than another object, but they're at the same velocity, then the one with the higher mass has the higher momentum. On the other hand, if two objects have the same mass, the one with the higher velocity has a higher momentum. All right. One other thing that you want to keep in mind for especially physics passages, but I've seen this come up in chemistry passages as well, is dimensional analysis. Okay, so in red here, it's a slight departure. Now, dimensional analysis, perhaps you've done in chemistry or in pre-calculus. And when you think of dimensional analysis, you think about changing units, right? Going from maybe miles per hour to meters per second, or back in stoichiometry, right? You would convert, for example, between a mass of some reactant and the volume of some product, right, with stoichiometry and then ideal gas law. But dimensional analysis at its heart is really just understanding that units in a calculation need to be consistent. Okay, so if, for example, I tell you, I assume you don't know very much about springs. I know I told you earlier, hey, the amount of energy stored in a spring is 1/2 kx squared, but what do you do with that? Well, okay, let's say I tell you, for example, that the force applied to a spring is 18 newtons. Okay, I just give you some value and importantly the units. And then I tell you, all right, well, K for that spring is 7 newtons per meter. And I want to know, if I exert a force of 18 newtons on this spring, right, how far can I compress it? So I've got a spring, and I exert a force of 18 newtons, and this has an intrinsic resistance to compression of 7 newtons per every meter. Well, how far can I compress it? Well, okay, Do dimensional analysis, right? If I start out with 18 newtons, I at least know that if I want to figure out the number of meters, right, I want to know the distance that I compress it, what's x, the number of meters that I can compress it, I can think about the units. Meters are in the denominator here, so if I take 18 newtons and I multiply by, well, there's 1 meter for every 7 newtons, these newtons cancel out and leave me with meters, right? So my assumption would be, all right, well, I can compress this spring 18 over 7, sorry, not newtons, just meters, right? That would be the distance of compression there. So use units to your advantage, right? Use units to your advantage. There may be instances in which you're given pressure, right? Pressure is force over area. You might not be familiar with that. That's okay. Make the units cancel out, and whatever results is probably the right value, okay? Last thing for physics, of course, is kind of the holy grail of physics, and that's Newton's laws, right? You need to know force is equal to mass times acceleration. Okay, force is equal to mass times acceleration. There's no more important, probably no more important statement in most physics problems than F equals ma. Okay, the units of mass, of course, are kilograms. Acceleration is meter per second squared. For those of you who've at least finished your first semester of Calc AB, you know that acceleration is the second derivative of position, or is the first derivative of velocity. Acceleration A is the rate of change of velocity, right? So that's dv over dt, or better yet, for those of you who haven't encountered that notation, right? It's change in velocity over change in time. Okay, change in velocity over change in time. So if I speed up, right, if I increase my velocity by 5 meters per second in 3 seconds, right, I change my velocity by 5 meters per second over the course of 3 seconds, then my acceleration would be 5/3 meters per second squared. If I wanted to know, for example, how hard I would have to push on something to give it that acceleration, let's say it's a car and I want to speed it up to 5 meters per second over 3 seconds, I know its acceleration, let's say its mass is equal to 2,000 kilograms, well then the force that I would have to push to bring about that acceleration is just that product, right? It would be 2,000 times 5/3, all right? So that kind of rounds out everything that you need to know so far as outside knowledge is concerned. Occasionally they'll throw a curveball on there and it'll catch you by surprise. What do you do for that? Do not go back and read your entire biology textbook and hope that you can, figure out everything there ever was to know about biology in preparation for the ACT. If you miss 1 or 2 questions due to outside knowledge, that's okay, right? You can still get maybe even a 36, but at least a 34 or 35, and overall still get a 36. So that really shouldn't be your primary concern for the science exam, but you should know all of these things regardless. Okay. I want to go back to what I said earlier about the rational functions. And just want to make sure that you know how to graph these on a calculator. There's one mistake that people tend to make, and I want to make sure we can shore up that you don't make that same mistake. Okay. So if I've got a rational function, let's say I want to graph, for example, y is equal to x minus 7 divided by x plus 4. This is not the proper way to enter this rational function into a calculator, right? X minus 7 over x plus 4. What the calculator is thinking is, okay, I want you to do x minus 7 divided by x plus 4. Okay, so if I graph this, I'm going to get something that does not look like the rational function I would expect. All right? Because I know from my input, I should have, if I'm dividing by x plus 4, I should have a horizontal asymptote of 1, because the degree of the numerator equals the degree of the denominator, and so that coefficient difference, that coefficient quotient there is 1. So I should have a horizontal asymptote of y equals 1, and then I should have a vertical asymptote at x equals minus 4. And I don't have either of those. It looks like I have a vertical asymptote at x equals 0, and there's no horizontal asymptote here. So we need to go back, and we need to make sure that we're entering that in properly. So make sure you're going x minus 7 quantity divided by x plus 4 quantity. And you need to do parentheses for both. This last parenthesis you don't have to put in, but just it looks nicer. So there we have a much better picture, right? I see that I've got horizontal asymptotic behavior around y equals 1. If we zoomed out a little bit, that would be even more obvious. And then I've got a vertical asymptote here at x equals minus 4. I'll do that actually. To zoom out, go to zoom, and then just zoom out, right? It'll go to the origin, just hit enter. That's kind of the focal point of your zooming out. Again, there it's very clear that we've got asymptotic behavior, both a horizontal and a vertical asymptote. Okay. If you want to know what the value of a function is, especially if you're plugging in multiple values, I think I went over this last week, but if I want to know what happens when I plug in x equals 7, x equals 9, x equals 10, right, because I'm guessing for answer choices, and I don't want to plug it in maybe 4 or 5 different times, then I can use a table, right? So I can go to table set, and I can ask for the independent variable, okay? And what that'll do for me when I go to the table is it'll give me the opportunity to plug in any x value, and it'll spit out the corresponding y value here. So this is my y1. Again, second graph gets me to the table menu. Once I go to that table, you'll notice here again in blue is y1. So let's say I plug in 5 for x, right? That'll tell me, hey, this is what I get when I plug in 5 for that function. If I plug in 7, that should give me 0, right? The numerator was 0. If I plug in -4, it's going to give me error, right? That's a divide by 0 error. Remember the denominator was x plus 4. Now, this minus 0.222222 here may look a little bit problematic. So if you go math frac, right, that'll allow me to convert that to, oops, I need to hit enter. And actually, I'll go to y1 up here, and I'll do y1. I think I can do is equal. This is a pain in the butt. Actually, this is not the best way to do to math frac. Let me get rid of that. We have y1 there again. Table set. Da 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 da. Okay. And no, I took away y1. I want to go over. Oh, I broke the calculator. Okay, if that ever happens, by the way, you get to a place where you don't know what's going on and you feel like you've done something wrong, quickly reset your calculator. If you've got any programs that you need to save, don't do this. But if you want to reset your calculator, go to second, plus, that goes to memory, and then 7, 1, right, all RAM, and then 2. That'll just do a quick soft reset of all the RAM, and you can get right back to where you were. So if I wanted y equals, let's just do x squared. Right, y is equal to x squared. And again, in my table set, I'm going to go to ask for the independent variable. That'll allow me to plug in any x value I want. Go back to the table. The whole point was, hey, plug in any x values, and it'll spit out the y value. Again, that way, if you're plugging in values for a formula, and you want to figure out, okay, well, is it f, is it g, is it h, is it j, is it k? You don't have to enter the whole formula in multiple times. You can just have the calculator reevaluate that formula for a number of different independent variables. Okay, let's go back to looking at some of the questions from some of the exams. So what we were looking at earlier was a science passage. And again, just to refresh that science passage, I was just looking at the very first one from B5. And B5 is the exam from December. That's going to make that real big here. December of 2018. I already went through at the very beginning answers to the first couple of questions. So now I want to finish going over the rest of the questions on that same passage. Usually that first passage is a little bit easier than the others. Let me go ahead and move that to the left, and I'll bring in these questions, and we'll just move around the questions as need be. Okay, so there's questions 3, 4, and then we'll get to 5 and 6. So I'm just going to get back into it. So it says, suppose an additional trial had been conducted at the same temperature at which 1 through 5 were conducted. X and Y had each been 2 mole per liter. What most likely would have been the concentration of Z? Okay, so we want to look at trials 1 through 5 because that's what it told us to do, right? If it tells you to look at trials 1 through 5, look at trials 1 through 5. I can't tell you how many times I've had students trying to answer a question and they can't figure it out. They're looking all over the place. And I say, hey, just read the question again. And it says trials 1 through 5. They go, oh, okay, that's where I'm looking. So, you know, be vigilant about reading the questions. My goodness. X and Y were each 2. Okay, well, let's try and make some connections. Are there any places where X and Y are both 2 here? No, we don't see that. Okay, I want to know what Z would have been. Well, Z definitely varies here, but I do notice that K doesn't vary. And I told you earlier in terms of kind of thinking about background that if you're ever given a formula, and here's a formula, it's pretty likely that you're going to use it in some capacity. Okay, it said the same temperature, so kind of no funny business going on. The only difference is that we're altering the initial concentration, or rather the equilibrium concentrations of X and Y. Well, K is an equilibrium constant that looks to be 0.10, so hey, K 0.10 equals Z over the product of X and Y. Well, X and Y are 2 and 2, so that would suggest to me that if I multiply that over, Z is going to be 0.4. Okay, all of the units are the same, so you don't have to worry about that, right? That's molar concentration. Don't make a value, or don't make a question rather, tougher than it needs to be. Plug things in. Again, if they give you a formula, always keep that in your mind as an option for solving a problem. Okay, looking at number 4, it says based on tables 1 and 2, so you better look at tables 1 and 2. How many trials were conducted at the temperature above the freezing point of water? So here you need to know the freezing point of water. Okay, you need to know that the freezing point of water is 32 degrees Fahrenheit, and the boiling point of water is 212 Fahrenheit. Or easier, obviously, and in this case, you'll notice that all of the temperatures are given in degrees Celsius. The freezing point of water in degrees Celsius is 0 degrees Celsius. The boiling point of water is equal to 100 degrees Celsius. So 0 and 100, right? So that's really easy to evaluate for Celsius. Importantly, I need you to know that freezing point and melting point are the same thing, right? Freezing point and melting point are the same thing because freezing point is the temperature at which you go from liquid to solid, right? Freezing point is liquid to solid. Well, that's the same temperature at which we go from solid to liquid. So again, freezing point and melting point, same thing. The same goes for the boiling point. The boiling point and the vaporization point, same thing, right? It's that liquid gas temperature boundary, okay, regardless of the direction of the change. Okay. So how many were conducted at temperatures above the freezing point of water? Now, in Table 2, they gave us the temperatures. Notice 0 is not above 0, okay? So I've got 1, 2, 3. Those are above the freezing point of water. And I don't see temperature anywhere in Table 1. So at this point, I need to go back and look at the passage to see what temperature these trials were conducted in. So let's see. Let's see. It says trials 1 through 5 were conducted at the same temperature. 6 through 10 were conducted at different temperatures. Okay. That doesn't tell me much, does it? It says, well, I've got to find some connection. Does it tell me anywhere else in Table 1 about temperature? So it doesn't tell me explicitly. So now I'm thinking, all right, well, I'm not screwed. I can still figure this out. I wonder if I can make any connections between the data in Table 1 and the data in Table 2. Again, I have hit a dead end, but I'm just going to turn because I have more options up my sleeve. Again, it's not stated explicitly. They ask me Table 1 and Table 2. Let me make a connection. Let me see if any of the data are the same. Well, I do notice that right here, 1, 1.5, and 0.15, that is the same as this row in table 2, right? 1, 1.5, and 0, 1.5. And of course, K is the same there. And K actually varies with temperature, right? K varies with temperature. So it looks like, because all of these were conducted at the same temperature, and trial 1 happens to match the conditions of trial 8, I think that all of these were conducted at a temperature of 10 degrees Celsius, which was the temperature of at least trial 8 in table 2. Okay, so it looks like these 5 and these additional 3 in table 2 were conducted at a temperature above 0, and so that leads me to choice H there. Okay, so that initially looks like it's going to be a difficult question because it doesn't tell us explicitly what the temperature was. No problem. Look for connections between the data and you're good. Let's look at 5 and 6 here. So I'll just bring 5 in and then we'll switch back between the two graphics here. So it says, consider the temperature data in table 2. Oh, okay, I only need table 2, so no problem. Did the reaction more likely reach equilibrium faster in trial 6 or trial 10? Okay, so a couple of things here. First off, sometimes you're going to find yourself at a total loss for explanations to the questions that they ask you. If you come across a question that gives you explanations and you don't know how to assess the data that they've given you, right? For example, I'm going to look at trial 6 and trial 10. I see some K stuff. The Ks are different. The X, Ys, and Zs are different. The temperatures are different. Okay. But I don't see anything about rate there. Right? And there's nothing in the passage, let me move this down, there's nothing in the passage that tells you about rate, right? Nothing tells you about rate. All it says is equilibrium is when the rate of the forward equals the rate of the reverse, but nothing about rate as it's going to change throughout the trials. So, let's look at the explanations in the actual answer choices and narrow down from there so that I don't have to just kind of, take a shot in the dark and hope that I can figure it out. So let's just see. Forget what the question is. Rate of a reaction is generally greater at a lower temperature. I'm going to think back to chemistry. If I heat something up, the particles are moving around faster. And so I would expect that a reaction would take place at a higher rate. And that would make sense to you, right? If you leave meat out on the counter, it'll cook if you leave it out for 10,000 years. But if you speed it up, if you raise the temperature, it'll cook in just a couple of minutes. Okay, reactions are much, much, much faster at a higher temperature. Right? Reactions are much, much faster at a higher temperature. So I don't like A, right? The explanation is wrong. And if the explanation is wrong, the answer is wrong, right? It can't have a right answer, but then a wrong explanation. It's got to be both. Now, looking at the explanation, if I look at B, the rate of a reaction is greater at higher temperature. That looks good, so I'll keep that as an option. And C is out because it says we're generally greater at a lower temperature. So I like B and D. So now let's figure out, if we accept that that's true, a reaction is faster at a higher temperature. I know that trial 10 has a higher temperature, 40 compared to minus 15. Let me clear some of the drawing that I've done out here so that you can actually see it. Oh, okay, that's a little tough to do. You get rid of that. Get rid of that, and get rid of that. Okay, so now you can actually see those temperatures. Okay, so definitely in trial 10, the temperature is higher, and so I would expect the rate of the reaction in trial 10 to be higher based on the assessment that we gave for the answer choices. Let me bring back up 5 and 6 there. 5 and 6 are there. Okay, cool. So again, we got rid of A, got rid of C, and it says, hey, which one would reach equilibrium faster? Maybe I don't know that it would reach equilibrium faster, but I know that a reaction is faster at a higher temperature. Okay, and the faster one. They're asking me for the faster one. Don't make it more complicated. And so that's going to, of course, be trial 10 there. Okay, last question on this passage. It says, assume that X, Y, and Z were gases. The boiling points for each one must be what? Okay, boiling point, boiling point. Okay, well, let's go back. What is boiling point, right? Let's start there. What is boiling point? Well, as I mentioned, boiling point is the temperature at which liquid turns into gas, okay? Or vice versa, right? Gas could turn into liquid. It would be the same temperature for both of those changes. Okay. It says they're gases in all of these trials. Well, let's think about this. Let's just assume G is right. I have no reason to do that, and actually G is not correct. But let's just assume G is correct. Let's say that we know the boiling points are 0, right? The boiling points are 0. Okay. If the boiling point is 0, then in each of these trials, I better be above that boiling point. Because if the boiling point is 0, right, that's the threshold, at 0, anything less than 0 on the number line, and we're going to be liquid. Anything greater than 0 on the number line, right, in terms of the temperature, and we're going to be a gas. So if they are gases, and it says they're gases throughout each trial, okay, they're gases throughout each trial, then all of my temperature values must be above the boiling point, right? I've got to be above the boiling point so that I can keep those substances as gases. Okay. Now the lowest temperature is -15. Remember, all of table 1 we determined was at 10 Celsius. So the lowest temperature is -15. And I know that has to be higher than the boiling point if they're indeed going to all stay gases. So if this right here, right, the kind of lower bound for boiling point is -15, then I know my boiling point has got to be even somewhere to the left of that, right? Because at -15, they're all still gases, and so I've got to be below -15. Okay? As a general rule, if you're thinking about keeping everything in one condition, right, or hitting some extreme, you're probably not going to get an answer like G or H here being correct, right, the ones in the middle. If ever you're kind of strapped for time, go for F or for J on a question like this, or A or D on a question like this. Go for the extreme environmental conditions, the extreme differences in independent variable. That way you're shifting everything in one direction. Okay, so that's a pretty common thing that'll come up. All right. So that's just one science passage, and of course there are many. I looked at, last week, I looked at a comparing different scientists' viewpoint, so I did a little work on that, and definitely next week I'll probably do something similar. I'd like to look at a reading passage. I've yet to do that, and let me go kind of a little bit older. I'll go to June 2017. This is Form 74C. And I just want to go through, I'll just take a couple of minutes, and let's go to, I'll just go to the third passage there. Okay, the quality here is not amazing, but it'll do. So let me bring that in here. Again, this is, now that would be tough to read. I'll make it a little bit bigger for us. This is passage 3 from the reading section of ACT 74C. Okay, now I'm going to kind of flip back between the questions and the passage, obviously, as I go. I want to make something really, really, really clear to everybody watching, and that's that if you're practicing for the reading section, the worst thing that you can ever do is to print out a practice reading section front and back. Okay, never do this to yourself. If you accidentally do it, you've wasted the paper, that's fine. Go and print it again. Make sure you always have passage on the left, questions on the right, right? That time that you spend in your practice flipping back and forth does not accurately mimic testing conditions on the day of the exam. You will not have a passage on the front, questions on the back. They will always be, so they'll fold out, passage on the left, questions on the right. So just make absolute sure you do this. Some of the tutoring places I've worked at, I've driven them nuts because I've made them reprint whole exams just because the passages and the questions were front and back. Don't do it. It's a total waste of your time. It's going to decrease your confidence. It's not going to give you an accurate idea of where your score is because you're not, again, adhering to the conditions of the actual exam. Okay? All right, let me tell you just how I go through the reading passages, and this is different from the way that some people go through it. And you know, it's important that you find a strategy that works for you. Not everybody works exactly the same way. But for me, this is the way that I go about the reading passages. I'm going to go ahead and lock this into place. That's what I want to do. It'll give me this nice little locking graphic, and I'm going to lock the questions into place. Sometimes Microsoft does fun stuff. I like that graphic when it comes up. Okay, cool. So I open up the passage, and again, I have the questions on the questions on the right and the passage on the left. So I open up this passage. The first thing that I'm going to do is just quickly skim the background. I know it's a little tough to read, even in high def. So just always read the background. It says using Native American folk tales in the classroom. This is from 2007. Make sure you know what year this is from. Make sure you know what year it's from. The way that you interpret passages that were written many hundreds of years ago is very different from the way you interpret passages that were written 10 years ago. Okay? So the first thing that I'm going to do is I'm actually just going to go to the questions. I'm skipping over question 1. Question 1 is almost always a main idea question, okay? If you read the passage and you don't know what the main idea of the passage is, you're not going to get most of these questions right anyways, right? You need to go and practice reading on your own, independent of the ACT a little bit more if you're having problems answering those main idea questions, okay? We'll cover them, but that's not something that I'm going to look at before I start reading the passage. Okay. Now, let me explain why I do what I'm about to do. The biggest issue that my students have on the reading section is I can answer like 7 of the questions really quickly. I can find the answers. Those are super easy. But there's just a few questions that I'll sit there and stare at for 5 minutes and not be able to find them, right? I'll scurry around, I'll scramble trying to skim back over the passage, but nothing, right? For the life of me, I can't find the answers to these darn questions. So it becomes really just a high-stakes hide-and-go-seek exam, right? Here's my thinking. If I'm going to play hide-and-seek, I want to know what it is I'm looking for ahead of time. Okay, you've almost all probably had this situation where you're studying for exam and you're studying for an exam and you say to yourself, man, if only I knew what questions were going to be on the exam, studying would be so much easier. Well, here you have the questions and the reading material in front of you. To me, it doesn't make sense to do the reading before you see the questions, right? Go to the questions first, okay? At most, take about a minute looking at the questions and look for very specific things in those questions, okay? Look for things that would be hard to find were it not for reading the question ahead of time, right? If you see a main idea question, that's not something you're going to want to find at a specific line, so don't worry about it, right? That's not something that should suck up any of your time before you go and do the reading, okay? So let me go through these. I don't think I've done this passage in quite some time. So looking at number 22, for example, it says, what's the main purpose of the first paragraph? I don't need to read the answers ahead of time. Looking at that question is only going to waste my time, okay? I might, if I want to, go and just make a note next to that first paragraph and say, okay, question 22, I'll just write a 2, save the time, right? It's all in the 20s. I know question 2 relates to that section, so then when I finish reading that first paragraph, great, I can go in and answer the question. And it actually says lines 1 through 24. It includes this block quote here. Okay, so after I read that, maybe I'll go ahead and go and answer 22. Okay, but no more assessment than that. Okay, number 23 says, the passage author most strongly suggests that a particular group would deem one of its own stories to be unacceptable if, during a telling, the storyteller what? Okay, the ACT is notorious for using exact wordings from the text in the actual questions, okay? When I see the word deem right here, right, when I see the word deem, that is a really, really, really big, I'd say, red flag in a good way to me, that if I see that word deem, I'm probably going to find my answer to this question. But okay, why would a group view its stories as unacceptable? Okay, that's a question you should focus on for about 4 to 5 seconds, and you may even want to write a note to yourself, deem unacceptable? right? Deem unacceptable. Why? Okay, move on, right? I just threw my stylus. Move on. Number 24, one function of the passage author's statement that her home pueblo is very different from the other pueblos in New Mexico is what? Now, if I'm looking at this question, the easiest thing to find is the word New Mexico, right? New Mexico is capitalized. It's going to stand out. My eyes will be able to find that very quickly. In fact, if I skim for it right now, I find that New Mexico comes up and features very prominently in this paragraph up here. Indeed, we're talking about the pueblo in New Mexico here. Okay, so I'm searching for pueblo in New Mexico, and why is it different, right? So I might want to make a note to myself right here. Why is the pueblo different here, and that's question 4, different here than it is in other pueblos of New Mexico? Okay, number 5. The passage author, bring that up, the passage author most strongly implies that whether the elders will approve a book for the children of the community depends on a book's what? Okay, so what will they approve, right? The elders approve, okay? And I know that she's talking about her pueblo here, right? So the pueblo elders should come up somewhere near the end, right? So when I find the word elders, right? When I find the word elders and approve, right? Those are the key words that lead me to my answer on number 5. So I might want to write a note to myself, right? Elders approve. And this doesn't need to be neat, right? The faster, the better. All right, elders approve of what? Number 26. So as she is presented, Silco indicates that one purpose of Laguna Pueblo hunting stories was to help hunters what? Silco, Is that something that comes up in just one small portion, right? I might want to search for Silco. Now, I'm skimming for it right now. This is not something I would do before the exam, by the way. But I'm just looking over. I want to see if Silco is a big deal. Now, here's the thing. Silco is actually the writer of this quote here and is the subject of the whole passage. So Silco is not what I want to focus on for this question. Okay, that's the reason that I'm searching for her name now. I want to know if Silco is important. It's not. So let me find something better from this question that I can focus on that will more likely lead me to my answer. Okay, purpose. The Laguna Pueblo hunting stories. You know what? That's what I'm going to look for, right? I know Laguna Pueblo is probably there somewhere. I've already seen Pueblo capitalized, but hunting stories, right? That's what I'm going to look for. I'll even make a note to myself right here. Hunting stories. Okay, again, very quick. Hunting stories. All right. Number 27. The passage author most directly connects her knowledge of the distinctions between and across American tribal nations to her experiences as what? Okay, what does she make a connection to? Her knowledge of distinctions, the differences, right, relate to her experiences what? Okay, I can't really figure out much from that question, but I'm going to hold it there, and maybe it'll make a little bit more sense after I read the passage. Okay, line 66, what does great mean? Okay, just go ahead and go and circle great and then move on, right? You don't need to do much work on that. 29 says, which of the following characteristics does the passage author most directly use as evidence of their diversity? Evidence of diversity, okay? How do we know that they're diverse? That's the key word there. And the passage author states that kivas are places she associates with what? So we're looking for the word kivas, right? All right, so diversity was another thing, right? Just to write that out. Diversity and kivas, whatever those are, okay? So if we find any of those things in the passage, we know that we've got answers to questions. Now, that assessment, right, I know I'm a little bit long-winded right now explaining that because I want to explain to you why I'm pulling out certain pieces of those questions before I go into reading the passage, okay? That whole assessment should take no more than maybe a minute or a minute and 30 seconds. A lot of students are really, really, really scared to do that because they think that's going to cost them time. I see it much more as an investment, right? You're going to invest that time up front, and it's going to save you time later on when you're trying to find a lot of these details in the passage, okay? If I know for ahead of time, for example, that I'm looking for the word kivas, well, when I see that in the passage, I'm not going to miss it, right? Because right before I start reading the question, I go back and I say, okay, Hunting stories. Okay, I'm looking for that. Diversity. How were they diverse? Why did the elders deem something unacceptable? What did the elders approve of? What are the kivas, and what does she deem unacceptable? Right, a group would deem unacceptable. Okay, now I know what I'm looking for, and so when I find those small details, they're going to really jump out at me in a way that they wouldn't beforehand. Okay, so do that assessment before you start reading these passages, and I think you'll find that the details come a lot easier to you. Now, one more thing is that this last paragraph, if you're searching for a question, right, you're searching for an answer to a question, and you, for the life of you, cannot figure out where it comes from, probably, if you haven't had a question that deals with the last paragraph already, the answer probably comes from the last paragraph, okay? When in doubt, read that last paragraph back to yourself and see if that reveals to you anything. 95% of the time, a passage has at least one question about the last paragraph, if not from the last line even. Okay, so I'm going to read that now. Depictions that are culturally acceptable at one pueblo are not necessarily acceptable at a different. As such, elders would say the book could be used with their children, while elders at another pueblo would disagree. It's not a question of cultural authenticity. It is one of appropriateness in teaching, given a specific audience. Okay, there's the answer to my question about what would the elders approve of, right? So I'm going to go back to that question. I can answer it now, right? What would the elders approve of? That was question 25, and it says, it depends on its appropriateness in teaching, given a specific audience, okay? So entertainment value, definitely not. Popularity, nope. Appropriateness, maybe. Representation of the worldview of many cultural groups. No, it says given a specific audience, right? Specific audience, that would be relevance to a particular group. I like C and I move on, okay? So 95% of the time, you're going to get a question from that last paragraph, right? I can go to any passage. If I've read the questions, I go to that last paragraph, I know I've got at least one answer. Even if it's one line, I'm going to get an answer from that last paragraph, okay? So read the questions ahead of time. Okay, I think for most people that ends up being a real huge boon for them, right? It really, really, really helps. If you find yourself struggling on a passage, nix it and go to the next one, right? Come back to it and then just try and search for small details as you go. But I think if you practice with looking at the questions before looking into the passage, you won't struggle nearly as much as potentially you have been, okay? The other thing with the reading is, of course, no matter what, if you're a slow reader, these passages are astronomically difficult. So how do you improve your reading speed? You read more, okay? And importantly, you need to read more on paper. Right? Reading on a screen is not at all the same. The way your brain works, it does not process reading on a screen the same way that it processes reading on an actual physical page. Okay? So print these out. If that's at all a problem for you in terms of cost, print them out at school. Ask a teacher to print them out for you because you're really trying your hardest to prepare for the ACT. I'm sure you've got at least one teacher who'd be willing to do that for you, hopefully all of them. Read things on a page. Right? The best thing that you can get to prepare for the ACT reading section is a library card, right? Go and check out some books at a library, whether that's your school library or your county or city library, what have you. Go and read more, even if it's things that you don't think the ACT would ever cover, right? If it's a biography of Michael Jordan, so be it. Just read something. The only way to bolster and increase your reading speed is to read more, so go and do that. That also kind of goes double for the science portion, right? A lot of the science exam is just the speed with which you can digest and process information. So read more and you'll be better off. All right, I'm Virgin on 5:30 here, so hopefully those of you watching now or those of you who end up watching a little bit later found this helpful. As always, I'll be back again next week at the same time, so if you've got questions, you want to leave them in the comments here, or pretty soon I'll post a link to what the page will be for next week's live stream. It should be at the same link as it was for today's live stream. If you've got any questions, let me know, and I'll do my best to answer them, and I'll see you then. Thanks for watching.